Hi everybody, my name is Umberto Follo and I'm a PhD student in Electronics and Telecommunication at Polytechnic of Torino. My doctoral scholarship is funded by the Italian National Institute of Nuclear Physics and my work is based on the design, simulation and test of monolithic CMOS sensor for timing applications. My research is inserted in a bigger project, the EECE experiment, which is a future CERN experiment that will take place after 2036. EECE is a next-generation heavy helium experiment. It will be composed of several silicon detectors, such as the time-of-flight system, which is needed to determine the particle produced in CERN collisions. The aim of my work is to develop a monolithic radiation sensor capable of achieving 20 picosecond time resolution. This means that we need to measure the particle in pigment time with an error of 20 picoseconds. This requirement has not yet been met by anyone over such a large area. Indeed, the experiment required a surface area coverage of about 40 square meters of silicon sensor. The solution proposed was to use monolithic CMOS sensor. In order to achieve the 20 picosecond goal, we start from the technology developed by the INFN Arcadia collaboration, which developed a monolithic CMOS sensor in 110 nanometer CMOS node. What does monolithic means? Means that we can implement the electronics and the sensor part in the same substrate. And hence we can have low material budget and a cheaper technology because it used a standard CMOS sensor technology. The Arcadia technology allows for fully depleted sensor and hence fast charge collection and also allows for large electrode, which means a uniform electric field. And for timing resolution, for good timing resolution, we need the uniform electric field. The drawback is that at present the time resolution is too poor due to the limited signal-to-noise ratio. So the idea was to integrate the LGAT concept, low gain avalanche diode, inside this technology by adding a highly doped p-type region called gain layer beneath the sensor pad. In this area, the electric field is high enough to trigger the avalanche process, and hence the signal produced inside the sensor is multiplied, which means a larger signal-to-noise ratio and hence improvement on the time resolution. We produced a first prototype with integrated electronics and gain layer, which is called MAPIX, or monolithic CMOS avalanche detector pixelated prototype. It is developed in 110 nanometer technology of LFoundry. It has an active thickness of 48 micrometer. It is based on an in-pixel front end working at 1.2 volt and output pixel buffers with buffer out the analog signal. It is a completely analog chip with 64 times 2 analog output, which buffer out the 8 matrices of 64 pixels each. The pixel size is 250 times 100 micrometer. For the experimental result, we received the first production in July 2023 with some problem with the noise at the beginning, but then it was solved and we achieved in October 2023 240 picosecond. Then we discovered that we had a very high substrate current of the sensor and we corrected that behavior with a focused ion beam. So we shorted a floating element that we forgot in the design. And we achieved 130 picoseconds with the same structure. Then we produced a first short loop, which are a new production of the foundry using the same mask set used for the first engineering run, but using a different doping concentration in the gain layer. And with that, we increased the gain and we achieved 75 picoseconds in October 2024. But how can we go to 20 picosecond? In 2025 is planned and is already in production a second short loop in which we change not the doping profile, but we change the thickness of the substrate, because from simulation we saw that from going from 50 micrometer thick structure to 15 micrometer thick structure, we can go below 20 picoseconds. Thank you very much for the attention and have a nice day.